Alright, so today's lesson is the chain rule. Hear the nice sweet sounds of Aretha Franklin in the background. Alright, this is another rule to help us find the derivatives of more complex functions. Alright, so let's look at this question right here. What is the derivative of this ugly function f of x is equal to x squared plus 1, all raised to the fourth power? So, if we want to just use our regular rules, we'd have to raise this thing to the fourth power and do all kinds of, let's say, just Pascal's triangle, expansion of the binomial using binomial theorem. That's going to be a lot, and you probably don't remember it. Plus, things can get a whole lot harder than that. All right, so let's take a step back. Let's do some stuff we do know. Okay? So let's look at this easier example. Instead of going to the fourth power, let's go to the second power. All right, well, if you remember, hopefully, if you say something squared, that means x squared plus 1 times itself x squared plus 1. All right, well, that doesn't look a whole lot worse. We could go ahead and distribute it out, find the derivative that way, or we could use product rule, which is what I'm going to try to do here. I'm getting to a point. I'm just trying to show you why this works. You don't really have to ever do this. All right, so when I take the derivative using the product rule, okay, if you remember the product rule, you take the derivative of the first. So the derivative of x squared plus 1 is 2x times the second one left alone, x squared plus 1, plus, leave the first one alone, x squared plus 1, times the derivative of the second, which is, again, what? 2x. All right, so if you look at that, we've got what? Two things that are exactly the same. So this is actually 2 times the x squared plus 1 times the 2x. All right, which I could, yes, go ahead and say is what? 4x times x squared plus 1, and I could multiply it through and get a better looking answer. But the key thing here is to notice this part because we're going to use it in the next example. All right, we good? All right, so let's take it a step further. Let's go to x squared plus 1 to the third power. All right, so we can rewrite that as x squared plus 1 times x squared plus 1 squared. We just took the derivative of that, so we're going to use a product rule again. We're going to say, all right, the derivative of this is equal to derivative of the first, which is 2x, times the second one left alone, x squared plus 1 squared, plus, leave the first one alone, all right, and then take the derivative of the second, which if we remember is 2 times x squared plus 1 times 2x. All right, so if we look at that, we've got 2x, x squared plus 1 squared. This one is secretly, rewrite this. This is secretly 2 times 2x. I just move the 2 up front, the 2x next to it. And I've got 2 of these, so that's x squared plus 1 squared. So I've got one of these 2x times x squared plus 1 squared. And I've got 2 of them there. So if I combine like terms, this gives me 3 times 2x times x squared plus 1 squared. Huh. That's interesting. So the previous one we had 2 x squared plus 1 times 2x. We're taking the derivative of something raised to the second power. Okay, so our power went down by 1. X squared derivative, that's 2x, and we had a 2 out in front. That's kind of looking weird. All right, in this one, we had a cube. The 3 came down here. That now became a square. That's almost the power rule. And then the derivative of that was 2x. All right, so if we take that same process, let's think about it. This one's probably going to be what? All right, it was 4th power, so we go back and look at our other ones. That power actually came down here. All right, we had this got x squared plus 1, but instead of raising the 4th power, that's going to give me subtract 1, kind of power rule-ish. Raise to the 3rd power. And then the derivative of this part, which seemed to pop up on those, ended up being 2x. All right, so let's see. We did kind of like a power rule on just this 4th part, but then we also have the derivative of the inside part. So we look all that together, we start to see a pattern, and that's where this next rule comes into play. It's the chain rule. All right, if you can see that there, the derivative of f of g of x, that's a composition, is equal to the derivative of the f with the g still inside times the derivative of the g. All right, it's often good to think about this like insides and outsides. Okay, we've got g of x is our inside function, and our f is our outside. So we got inside and outside. So we take the derivative of the outside, leaving the g alone, the inside, and then we take the derivative of the inside. Okay? I like to think about it this way. This is a little weird. All right, but if you have a pregnant woman, okay, this is like our composition function. Okay, you're going to take the derivative of the mom with the baby still inside times the derivative of the baby. All right, if you have looked at some of my videos from the past, from my calculus, I think 2 years ago, they did some stuff with this. All right, but again, it's just the derivative of the outside with the inside still in there times the derivative of the inside. Okay, and that's the chain rule. It's a really powerful tool to help us do some stuff. So let's look at a couple of examples. Let's look at this one. This would be horrendous to try to raise to the 5th power because it's not a binomial, so it doesn't really follow our Pascal's triangle. All right, but with the chain rule, we can do this pretty simply. All right, the derivative of this function, so y prime. All right, we're going to identify the inside and outside. Okay, the inside is this part right here. All right, so our inside, I'll write over here. You don't have to write this every time. But the inside, or the baby, is the x cubed plus x minus 1. All right, and then the outside, all right, is just something raised to the 5th power. You see that? We got the inside, which is inside of this outside part. All right, so if we follow the chain rule says, let's take the derivative of the outside. Okay? So if this is something raised to the 5th power, using the power rule on that, we bring the 5 down. All right? And then we subtract 1 from the 5 for the power, it becomes to the 4th power. Okay, but that inside stuff is still there, so we're going to rewrite that as x cubed plus x minus 1. So we just took the derivative of this to the 5th power, brought the 5 down in front, subtracted to the 4, and then the inside, which was there, is just left alone. All right, and then the other part of the chain rule is once you do that outside, you got to take the derivative of the inside. All right, so this should be a pretty simple power rule. It's going to be times, because that's what chain rule says, and the derivative of x cubed, set it correctly, is 3x squared. The derivative of the x is just plus 1, and the minus 1 goes away because its derivative is 0. And that's the derivative. Okay? And feel free to leave your answer like this. There's no point in trying to multiply that out because it's just going to be horrendous and ugly and you're going to make mistakes. I would make mistakes. And that's just prettier this way. All right, so that's a basic one where the outside is raising to a power. You'll see that a lot, especially when we get into some other functions we can take the derivatives of, like trig functions and natural log. You'll see these come into play. All right, let's do another example. We need to find the derivative with respect to t, so we just changed our variables a little bit, of the square root of 100 plus 8t. All right, so let's rewrite this. Our function here itself, instead of saying the square root of 100 plus 8t, let's write that as 100 plus 8t raised to the 1/2 power. Anytime I see a square root, I'm probably going to rewrite it as a 1/2 power so I can use the power rule. All right, unless you're just really, really comfortable with it and just know what to do. All right, now we can identify our inside and outside. Our inside is that 100 plus 8t. Our outside is something raised to the 1/2 power. So let's apply our derivative, our chain rule. So our derivative of this function, chain rule, derivative of the outside, the derivative of the mama with the baby still inside. So power rule, the 1/2 comes down. We rewrite the inside just like it is, 100 plus 8t. All right, and then we subtract 1 from the exponent. So 1/2 minus 1 turns into negative 1/2. So we're doing the derivative of the outside with the inside still there. Derivative of the mom with the baby still inside. All right, then we say times, put a big old bracket for the next part, the derivative of the inside. The inside is just 100 plus 8t. Derivative of 100 goes to 0. Derivative of 8t just goes to 8. All right, and that's it. We can clean this up a bit by doing some obvious simplifications. What's half of 8? Kind of put those numbers together, that gives me 4. And I can either leave it written like this, or since it's a negative, it moves it to the bottom, and the 1/2 becomes a square root. So our answer, without fractional or negative exponents, is 4 over the square root of 100 plus 8t. All right, and that's how you do one with square roots. All right, a couple more examples here. All right, now that we know the chain rule, we can put it together with a whole bunch of other things. So let's look at this horrible example here. It's not horrible. It's really not that bad. All right, so we got a derivative. We want to take the derivative of this function, which is x cubed times the square root of 4x plus 1. All right, so what you got to train yourself to see is look for parts. So I kind of said it out loud. This is x cubed times, and I'll rewrite this as 4x plus 1 raised to the 1/2 power. All right, that times tells me something here. That tells me I got one part, one function, times another part, another function. So this is going to tell us this is going to be a product rule to start off with. All right, so we need to go back and review our product rule. Product rule says take the derivative of the first. All right, the derivative of the first is going to be real easy. Derivative of x cubed is 3x squared. And leave the second part alone, so 4x plus 1 raised to the 1/2 power, or I'm just going to rewrite it as the square root of 4x plus 1. Plus, other part of the product rule, leave the first part alone, x cubed. And now we're going to take the derivative of the second part, which that includes a chain rule. All right, so we got the outside is something raised to the 1/2 power. The inside is 4x plus 1. So if we do that, we're going to say times. All right, the 1/2 comes down because of the power rule of the outside. Leave the 4x plus 1 alone. Subtract 1 from the 1/2, which gives me negative 1/2 power. So that was the derivative of the outside with the inside left alone. And now we take the derivative of the inside. The derivative of 4x plus 1 is just 4. All right, so let's clean it up just a little bit, make our answer look a little prettier. We rewrite 3x squared times the square root of 4x plus 1 All right, we have a half and we got a 4, so half times 4 is 2. We got an x cubed, so we can write that as 2x cubed. And the negative brings it to the bottom. The 1/2 makes it a square root, so over square root of 4x plus 1. And that is your derivative. Looks ugly, but it didn't take that much. We just had to use product. And over here, we had to talk about the chain rule. Okay, and that's going to be the most difficult part, is figuring out when to use what rule. All right, you just got to see it. Times means a product, and within that product, the derivative of this part involved a chain rule. All right, let's look at another one like that. All right, ooh, I've got a division sign. I got a fraction bar. So this should point out right away that this is going to be a quotient rule overall. All right, so low D high minus high D low all over low low, if you remember that from the last video. So let's think about it. All right. I might run out of room here. I apologize if I do. So derivative for a quotient rule is low. So we rewrite the x cubed plus 1 squared. D high, so the derivative of the 8x, which is 8, minus the high, which is 8x. And now when you take the derivative of the low, well, this low part is going to be a composite function. It's x cubed plus 1 inside of something squared. So we've got to do the chain rule. All right, so again, the outside is to the second power. So we say, all right, that 2 comes down. I rewrite my x cubed plus 1 inside there. And then I subtract 1 from the exponent, so it becomes just to the first power. Or I don't even have to write it. So that's the outside part. And then we also need to take the derivative of the inside. The derivative of x cubed is 3x squared. All over the whole bottom, x cubed plus 1 squared. And since it's low, low, we actually have to square that yet again. All right, so low D high minus high, or D low, use the chain rule. And then we're left, rest of our quotient rule was the low, low. All right, let's clean it up. All right, so we start to realize we got an 8 times x cubed plus 1 squared minus, all right, we've got an 8, a 2, and a 3. Hopefully I've done this all right. So that's going to give me 48. X and x squared give me x cubed. And I'm going to rewrite that x cubed plus 1. All over, if I square a square, I just add, or excuse me, multiply those exponents. So that gives me x cubed plus 1 raised to the 4th power. All right, some of you might ask, well, why didn't I just go ahead and distribute that through there, or distribute that through there? Okay, well, the thing is, just start looking at it. Notice some stuff. Okay, another part of calculus and math in general is just noticing things. So look up top. I've got x cubed plus 1. This is squared. And here I've got an x cubed plus 1 just to the first power. And on the bottom, I've got x cubed plus 1 raised to the 4th power. So this term, and this term all have at least one x cubed plus 1. So what I can do is I can just cancel most of those out, or a lot of those out. So we'll go back and through and say, all right, I've got one of them here, so that goes away. If I take 1 away from there, I'm going to take 1 away from there, so that goes to the first power. If I take 1 from each of those, I'm going to take 1 from the bottom as well, so that becomes to the 3rd power. And so our final answer here is 8 times x cubed plus 1 minus 48 x cubed all over x cubed plus 1 raised to the 3rd power. Oop, I said final answer. All right, but we actually could do one other quick simplification. If I distribute through there, that gives me 8x cubed. I've already got a minus 48x cubed. So if I put those together by combining like terms, that gives me a minus 40x cubed. We multiply through, distribute with the 8, so plus 8, all over x cubed plus 1 cubed. All right, and I went ahead and distributed because it was easy simplifications to do, and not all the terms had the x cubed plus 1, so I knew I couldn't cancel anything else out. All right, we good? If not, rewind, go back and look at it. All right, a couple more here. We got this one, I think one more. So this one, again, it looks very similar to the last one, except there's not. Last one had an x up top. This one doesn't. All right, so we could call this a quotient rule if we really wanted to. Actually, again, remember me saying key to part of this is just noticing some stuff? So since it's just an 8 up top, I could actually rewrite this as an 8 coefficient and then rewrite this as x cubed plus 1. Instead of a second power on the bottom, I could rewrite it as a negative 2 power up top. And now we don't have a quotient rule, we really just have a chain rule with a coefficient out front. All right, so let's do it this way. We take the derivative of this. All right, we got the coefficient out front, so just leave it there. All right, and then we talk about our chain rule. Chain rule, I bring down the outside exponent, so it becomes a negative 2. Leave the inside alone, x cubed plus 1. Subtract 1 from the exponent, so the negative 2 now becomes a negative 3. Careful on subtracting with negatives. And then we take the derivative of the inside. X cubed gives me 3x squared, and the 1 just goes away. So we have that. All right, clean it up a little bit. I've got 8 times negative 2 times a 3. So that'll net me a negative 48. I've got the x squared along with that. And now that negative exponent I can actually bring it to the bottom. This turns into x cubed plus 1 raised to the 3rd power. All right, and it looks a good bit like our last answer. Just a little bit better because we didn't have the x up top. All right, so that's using chain within other rules. All right, we got one last example. We got multiple chains. Okay, so my mama baby example kind of falls apart here because now we got a mama with a baby, with possibly a baby inside. Okay, so that's a little weird. It does happen every now and then medically, where somebody absorbs a twin. But yeah, that'll be a fun YouTube search there. All right, so let's look at this thing. Let me write it a little bit bigger so that I can read it and you can read it. F of x is equal to, inside this huge thing, I've got an x squared plus 4. It's square rooted, so I'll change it to 1/2 power, minus 3x squared. And that whole thing is being raised to the 3/2 power. All right, so I've got a chain rule. I've got an outside, which is raised to the 3/2 power, and an inside, which is pretty complicated. Okay, so let's just take it baby steps. Baby steps. All right, chain rule. The outside is something raised to the 3/2 power. So we do our derivative. Our huge outside one is something raised to the 3/2 power. So it gives me 3/2. All right, then all of that stuff inside, which I'll rewrite as the square root of x squared plus 4, I'll just leave it alone, minus 3x squared. All right, and I subtract 1 from 3/2, which gives me 1/2. So that was the derivative of the outside. All right, now I'll take the derivative of the inside. Okay, and remember the chain rule, I'm multiplying. So I'm going to have a huge part because my inside's pretty complicated. I'm going to have a huge thing multiplying by this outside part. All right, so let's take a derivative of the inside. Ooh, we got another stinking chain rule. Yeah, we got something raised to the 1/2 power. So we do a chain rule on that. We bring the 1/2 down. We leave the x squared plus 4 inside. Subtract 1 from the 1/2, which gives me negative 1/2. All right, and then we do the inside there, which gives me 2x. So we've just done the chain rule on that part. And then we have a minus this, so this is just like addition rules, which is take the derivative of the first, minus the derivative of the second. And so we take the derivative of that, which is going to give me a minus, just a simple power rule, 6x. And that is the derivative of the inside, which also in itself had a chain rule. All right, let's see if we can clean this up a little bit. It might not look any better. We'll do some obvious simplifications, like we could multiply the 2x by the 1/2 to bring it out front. And that might be enough, but let me just go ahead and simplify it all I can. We got 3 halves. This whole thing is raising to the 1/2 power, so that actually becomes the square root of the square root of x squared plus 4 minus 3x squared. That might not look prettier. All right, times all of this stuff, which let's see, 1/2 times the 2x leaves me with an x, over, negative brings it to the bottom, 1/2 makes it a square root, so the square root of x squared plus 4, and then minus the 6x. Yeah, it doesn't look very much prettier. But you definitely could see your answer written in this way, or a combination of the two. Probably most of the time it's going to happen, maybe this will just become an x out front instead of 1/2 and the 2x. All right, but that's a multiple chain rule. All right, so that's all I got for you. Okay, take a look at these 4 problems here. And bring them to class, and we'll look at more examples, some more complicated ones, and get you to work then. All right, good luck.